this is your hacker nickel wife Cyan. Welcome to the stream. Welcome Midnight Drifter. Welcome to it. Welcome Mr. Lucas. Welcome underscore. Welcome Adam. Welcome Batomi. Welcome highly intelligent Owen. 大家好，冰吗 I still struggle to pronounce your name. Is it Jesus or Jesus? Jesus. Hello. Welcome, Furen-san. Welcome, Kiran. Hello, everyone. Welcome, Hannibal Feeder. Oh, you guys been waiting for this one? You guys been waiting for this one? You guys love pointers? I'm a little sweaty on my balls. Because I don't remember much about pointers. It's 1 AM. Listen to me to sleep. The pointers are going to calm you down. Welcome, Gavin. Hello. I don't know what pointers are, so I'll be learning something new. Whoa, nice. Nice. I don't know if this is a good starter, beginner guide to pointers. I feel like in other language it's a little different. And what? I'm a paws. I'm a cat, so I technically have paws, not balls. I don't have balls. I have a tail that looks like a ball, but I don't have. Yeah, you know what I mean? You know what I mean? I'm a total noob. Let's go. Let's go. Let's not make ourselves noobs. We'll come out of this very smart. Very smart. Come now and pointers don't go together. Okay, good night. Good night. Thank you for coming. I don't know too much programming, but today we are all going to learn about smart pointers. A pointer is a general concept for a variable that contains an address in memory. So pointer is a variable that contains address. This address refers to or points at some other data. So pointer points. That's easy, right? You guys now all know pointers. A pointer is something that points to another data. I point to you. This is the language of love in programming. The most common kind of pointer in Rust is a reference. References are indicated by the ampersand symbol and borrow the value they point to. Oh yeah, we've been using that all the time. We use the ampersand and borrow the value. They don't have any special capabilities other than referring to the data. Also, they don't have any overhead and are other kind of pointer we use most often. The pointers don't have overhead. Okay? Oh, so those pointers, the references, they don't have any special capability other than referring to data. And they don't have overhead. And then we most commonly use the references, the pointer. So first, reference is a pointer. And we use them the most. And today we're not just talking about pointers. Specifically, we're talking about smart pointers, which are data structures that are not only act like a pointer, but also have additional metadata and capabilities. So they're smart. We're dealing with some smart stuff. The concept of smart pointer isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointer defined in the standard library provide functionality beyond that provided by reference. So C++ originated the concept of smart pointers, and Rust have different smart pointers that does amazing stuff. One example that we'll explore in this chapter is reference counting smart pointer type. So there's a smart pointer type called reference counting. It probably will count number of reference. So it's kind of smart. It knows how to count. An infant probably doesn't know how to count, but our smart pointer knows how to count. That's very progressive. Hello, Edmed. Welcome. This pointer enables you to have multiple owners of data by keeping track of the number of owners, and when there are no owner, it cleans up the data. So it checks how many owner of the data exist, and when there are no owner, the data will be cleaned up. So it's a very smart pointer called reference counting smart pointer. In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers is that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to. So regular pointer, they do not own the data, they borrow the data. But the smart pointers, they own the data. They're smart, so they own their own stuff. I've heard of smart pointers in C++, but I haven't used them and don't know what they are. Me neither. I don't remember learning them. I don't remember learning C++ smart pointers. Smart pointers are just a utility to automatically release a resource that is managed through a pointer, like a heap allocated data or file handles. Oh, thank you, Alex. So it's kind of like the same thing in Rust. It helps manage the release of a variable, of a resource. So we don't forget about cleaning up. Smart pointers are supposed to help with auto-freeing memory and stopping you from getting new pointers dereferenced. So I feel like it's a main thing of Rust. It's about freeing up the memory exactly when it needs to be done, to reduce the problem of like memory issues. Welcome, Mitama. Hello. Welcome, Jam. Well, and thank you, underscore. Okay. So smart pointers on the data they point to. What? We have already used some smart pointers? String and vect are smart pointers? I didn't know that. Both these types count as smart pointers because they own some memory and allow you to manipulate it. So string and vect own the data, and we can manipulate it. They also have metadata and extra capability or guarantees, such as string ensuring the data will always be valid UTF-8. Oh, so string and vectors, they are smart pointers. We have been using them already. I wish C++ programmers know how to manage memory. We have so many memory vulnerabilities. Is that why people are rewriting things in Rust? So there are less memory vulnerabilities? Instead of doing something like malloc then free in C, you only have to do malloc. The free will be called when it is appropriate. That makes... Wait, does C have smart pointers too? That would make everything so much easier. But C have smart pointers. You cannot do small pointers in C because it does not provide necessary syntax. Oh, poor C. So far, we know C++ has it. Hello, Maria-san. Welcome. What can string allocate on a heap? That's why they're small pointers. Ooh. And welcome, Porfia. You can write memory save code in C++, but it's much more easier in Rust because the compiler will yell at you if you do something stupid. I want to be yelled at. I really want to be yelled at by the Rust compiler. C has not small pointers since you usually need generic and destructors. Ah. Poor C. Poor C. Just do a lot of people still programming in C? It feels so sad. Okay. Small pointers are usually implemented using structs. The characteristic that distinguishes a small pointer from an ordinary struct is that small pointers implement the deref and drop traits. So small pointers have two traits. They have deref and drop. They probably have more, but those are somewhat important because deref allows an instance of the small pointer struct to behave like a reference, so you can write code that works with either reference or small pointers. What? Deref allows an instance of the small pointer struct to behave like a reference, so you can write code that works with either reference or the small pointer. I think it's going to talk more about it later in the chapter. This is just an introduction. It looks like the instance of a small pointer struct can behave like a reference. And the drop trait allows you to customize the code that is run when an instance of the small pointer goes out of scope. Oh, so this allows us to customize what happens when we need to drop the small pointers. In this chapter, we'll discuss both traits and demonstrate why they are important to small pointers. Given that the small pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing small pointer. Many libraries have their own small pointers, and you can even write your own. We'll cover the most common small pointers in the standard library. We're going to cover box T for allocating values on a heap. I think this is reference count, a reference counting type that enables multiple ownership. So that's another small pointer. A ref and ref mute access through ref cell, a type that enforces the borrowing rules at runtime instead of compile time. In addition, we'll cover the interior mutability pattern, where an immutable type exposes an API for mutating an interior value. What? So an immutable type can actually be mutable somehow? This is blowing my mind. What the heck? We'll also discuss reference cycles, how they can leak memory, and how to prevent them. Okay, that sounds so fun. 欢迎李妮，欢迎李妮。Why do I move? Cause I'm mutable. Welcome, Hapnia. Sorry, it's M for the Rust compiler. Yeah, just for the Rust compiler. I'll be S for C++ compiler. C++ is very lenient to a fault sometimes, which causes frustration to programmers because they accidentally introduce vulnerability. I remember dealing with what was it? It's not index overflow. It was like something. Segmentation fault, and it drives me crazy. It drives me crazy. What? I pronounced your name right? Prof Dia? Nice. I'm happy that my English is improving. Hello, Arrow. And we have Alok and Defer. Ref Cell is magic? I've never seen it. I wanna see the magic. I'll save moments. Are we talking about memory leak? I've read the whole Rust programming language, but because I never used Rust, I forgot it all. It's a warning for me. I need to use it somehow to remember all of this. Okay, let's dive in. What do we have now? We have this box. We're gonna be boxer. Cause pointer, point, boxer, box. What have I been talking about? Okay. Using box to point to data in a heap. So we're learning box, which is the most straightforward smart pointer. And the type is box T. Box allows you to store data on a heap rather than on a stack. Okay? What remains on the stack is the pointer to the heap data. Boxes don't have performance overhead, other than storing their data on a heap instead of on a stack. But they don't have many extra capabilities either. You use them most often in these situations. 1. When you have a type whose size can't be known at the compile time, and you want to use a value of that type in a context that requires an exact size. So if we have a type and the compiler doesn't know the size, and we want to use a value of the type in a context requires an exact size, we can use a box. When you have a large amount of data and you want to transfer ownership, but ensure the data won't be copied when you do so. So we want to transfer ownership. But we don't want the data to be copied. When you want to own a value and you care only that it's a type that implements a particular trait rather than being of a specific type. When I want to own a value and you care only that it's a type that implements a particular trait. Those feels like puzzles. I wanna see examples. We'll demonstrate the first situation in the enabling recursive types with boxes section. In the second case, transferring ownership of a large amount of data can take a long time because the data is copied around the stack. To improve the performance in this situation, we can store the large amount of data on a heap in a box. Then, only the small amount of pointer data is copied around the stack. So we store the large amount of data on a heap in a box. So there's only a small amount of data copied around a stack. And this is going to improve the performance. When we have a large amount of data, we want to transfer the ownership. Welcome, Programming Indonesia. Hello. Boxes don't have performance overhead, technically true, since the impact is minimal. But if performance is really important, you want to avoid heap allocation as possible. Do I use reference in that case? Box dynamic Neko. You put a cat in a box, it might disappear. You don't know if it's alive or dead. Okay, what do we have here? The third case is known as a trait object, and we have an entire chapter dedicated to it. Okay, I'll save it for later. The cat will put itself into a box. That's so correct. That's so correct. We love boxes. I'll put myself into a box spot pointer. Box dynamic neko will accept any type that implements the neko trait. So any neko can be put into a box. This is like the most beautiful code I've ever seen. I wanna make this into my next username. That's so cute. That's so cute. I'll never forget this. Then. There is the indirection of always having to access data through a pointer. There's the cost of finding sufficient space when allocating, and the CPU's cache doesn't like if data is spaced out far. What is indirection? Indirection is the ability to reference something using a name, reference, or container instead of the value itself. Oh. Hey. Not pointers were made for you. It's made for cats. Scordinger's box. Yep, never can pronounce that. Similar to performance impact of a linked list compared to an array. Interaction is like having to derive something to get a real value. Ooh. Indirection means having to follow a pointer to get an actual value. Oh, because pointer is like a direction. I see. Indirection refers to the fact that what you have on the stack is a pointer, not a value. What you have on the stack is a pointer, not a value. Which means that it needs to fetch data from a different location, hurting cache locality. Oh, cache locality. Oh, now it's starting to make more sense. It is saying the more we use pointers, the cost of finding the space to allocate the value will be high. And CPU cache doesn't like it if the data are spaced out far because of the cache locality thing. You want data to be close, so the most of it can be fit into one cache line. Ooh. Now I realize those computer organization clauses actually are useful. Accessing data from RAM is much slower than from cache. Ooh. Ooh, we're diving deep. Nice. Nice. So we only use pointers when we have to. Is that a takeaway? Okay, using a box to store data on a heap. Before we discuss this use case for box T, we'll cover the syntax and how to interact with values stored within a box T. Okay, so what do we do? What do we do? Let B equals to box new 5? So what do we have here? We have a box that has a value 5. And if we print it, is it going to show the location? Or is it going to show 5? Oh. Okay, let's run it. What is it gonna say? Kakoro. It says 5. It says 5. It says 5. That's why iterating over an array can sometimes be faster when the algorithm said it should be slower because of the CPU caching array. Oh, that's why sometimes I submit result for LeetCode. It gives me like strange performance percentile, even though like my solution is supposed to be really quick. Is the performance, the time limit, the actual time used is like pretty high, and vice versa. Oh, they're cache unused. Pretty sure you need to ask it to show location while some formatting thing. Ooh. If you want the pointer value of the box, use P. Does that stand for pointer? So if I want to see the location, it is showing the locations. It is. Here we are. Here we are. We have the location. Thank you, Alex. Yeah. Yeah. We just have our tongue out. No. I think this should stand for pointer. Nice. So we define a variable b to have the value of a box that points to the value 5. The variable b have the value of a box that points to 5. We can access the data in the box, similar to how we would if this data were on a stack. When the box goes out of scope, it will be deallocated. The deallocation happens for the box and the data it points to. So both the box on the stack and the data on the heap will be deallocated. B equals to A. B equals to a pointer to value 5, which is stored in an allocation on the heap. So 5 is stored on a heap, and the box is stored on the stack. Think. Putting a single value on the heap isn't very helpful, so you won't use the boxes by themselves in this way very often. Having values like a single 32-digit integer on the stack, where they are stored by default, is more appropriate in the majority of the situations. Okay? So, how will we actually use it? We can look at a case where boxes allow us to define types that we wouldn't be allowed to if we didn't have boxes. Okay. So we can enable recursive types with boxes. Recursive types. Welcome, Matsup. Hello. Hello. Recursive types. Let's go. At compile time, Rust needs to know how much space a type takes up. One type whose size can be known at compile time is a recursive type, where a value can have as part of itself another value of the same type. So a type has What? A value can have as part of itself another value of the same type. Is this English? Oh wait, it is English. A value have another value that's of the same type. Because these nesting values could periodically continue infinitely, Ross doesn't know how much space a value of a recursive type needs. However, boxes have a non-size, so by inserting a box in a recursive type definition, you can have recursive types. Oh, that's why you guys keep mentioning lists. A node has another node. Oh, okay, linked lists. We can iterate from the head to next. It talks about the con list too, like Haskell. It's the cons list. What is cons list? Which is a data type common in functional programming languages as an example of recursive type. The cons list type, well defined, is straightforward except for the recursion. Therefore, the concepts in the example we'll work with will be useful anytime you get into more complex situations, including recursive types. So, in Rust, if we build linked list, if we build doubly linked list, if we build graph with nodes, we gotta use the recursive types. Is that what it is? It's a linked list node. It has a value, a pointer to next cons list. But why the cons list instead of single linked list? Oh, I'm sorry for hurting people's eyes. What's the difference between cons list and linked list? Difference between cons list and linked list. The cons thing is a specific kind of linked list, namely singly linked list. Also, it's the same thing as the singly linked list. Maybe? Let's look. Oh, it's from the Lisp programming language, and it's dialects. In Lisp, the cons function, short for construct function, construct a new pair from its two arguments, which usually are a single value and another pair. These pairs containing pairs form a list. So we have a cons function that constructs a new pair from its two arguments, which is a value and another pair. Makes sense. Oh, what? Cons list is the fundamental data structure for Lisp. Maybe one day we'll learn Lisp. There's a great Rust tutorial called Learning Rust with entirely too many linked lists, which is pretty funny and educational, mostly about how difficult linked lists are to do in Rust. Now I remember, if I have a linked list program in an interview, I'll never use Rust. Okay, what do we have? The cons function concept has made its way into more general functional programming jargon. To cons x onto y. Informally means to construct a new container instance by putting the element x at the start of the new container, followed by the container y. Each item in a cons list contains two elements, the value of the current item and next item. The last item in the list contains only a value called no. without the next item. A const list is produced by recursively calling the const function. The canonical name to denote the base case of the recursion is null. Note that this is not the same as the null or nil in chapter 6. Wait, what? This is not that. This is the base case, which is not invalid or absent. I really want to see a diagram. Does it have a diagram? It has. It has. The big cons has. This is like the Russian doll. Do you guys know what I'm talking about? Like the... I know it's recursion. Yeah, I think the name is Russian doll. Matryoshka. I think my grandma bought me some of them. Thank you, and then posting the linkless tutorial. Be sure your parentheses keys are ready. I'm not ready. I'm not ready again. That's... Look at those. They look like cribs. They look like Lady M. They are layers and layers of parentheses waiting for me. I'm not ready. If a Ross interviewer asks about doing a linked list, they're probably wanting you to say don't do that more than they wanting an explanation. Nice. I found the perfect answer for an interview. Nice. Linked list has nil at the very inside. Ooh. Learning Russian with Cyan? No. I don't know Russian then. I know pivot. That's the only one I know, and I'm not sure if it is right. Okay, we know what a cons or... Do we know what cons is? Is that how we say it? Is that how we say it? So... we have an enum of list. We have cons. We're putting list into list. And looks like this is not okay. Because the recursive type list has infinite size. It even says recursive without indirection, so it's like pointers. Give me smart pointers. Insert some indirection to make the list representable. This compiler is yelling at me. Oh, what's right to do? Using the list type to store list 1, 2, 3 will look like the calling here. Oh wait, what are we doing? That list equals to cons 1, cons... Oh, parentheses. Those parentheses are killing me. And eventually, no. And it's not happy. Are we not doing this? Remove the comments. Oh, okay. So this is using that. I was so dumb. I was dumb. Looks like... Yeah? Okay, so what's the problem now? The first cons holds value 1 and another list value. This list value has another cons value that holds 2 and another list value. And then the one that has 2 has a cons of 3 that holds 3 that has cons. Wait, the one that has 2 has a cons that has 3 and no. And if we try to compile, don't worry, just follow it. Oi. Okay. What's gonna happen? What's gonna happen? It's the same arrow. Yes, I ran into the same arrow. The recursive type has an infinite size, so we need to give it some size. Help! Insert some indirection to make list representable. So it says the type has infinite size because we define list with a variant that is recursive. It holds another value of itself directly. The list has a list and is recursive, and we don't know the size. So how does Rust know how much space it needs to store the value of a non-recursive type? Computing the size of a non-recursive type. So we used to have a message enum that looks like this. To determine how much space to allocate for this, Rust goes through each of the variants to see which variant needs the most space. It says quit doesn't need any space, move needs 2 integer values, write needs a string, change color needs 3 integer values. The most space a message value will need is the space it would take to store the largest of its variant. So you just find the space of the largest variant. In this case, maybe it's this. And we'll assign that much space for instance. Contrast this with what happens when Rust tries to determine how much space a recursive type like the list enum needs. The compiler starts by looking at the cons variant, which holds a value of type integer and a value of type list. Therefore, cons is an amount of space equal to the size of an integer plus the size of list. And then this process continues infinitely. So we can use a box. We can put them into a box to get a recursive type with a known size. Rust can't figure out how much space to allocate for recursively defined types, so the compiler gives the arrow, and the arrow includes a helpful suggestion. of inserting some direction. It even does it for us. So we put a box for the list, but I'm really curious how much space. How does it decide how much space to be assigned for boxes? Welcome, Jax. Welcome to Neko. Hello. Indirection means instead of storing a value directly, we'll change the data structure to store the value indirectly by storing a pointer to the value instead. Because box T is a pointer, Rust always knows how much space a box T needs. A pointer's size doesn't change based on the amount of data it's pointing to. So they put the uncertain amount of data in the heap. And now Rust know, hey, you only got one box, and a box is just a pointer size, which is a fixed size. This means we can put a box T inside the const variant instead of another list value directly. So I put box T in a const variant instead of a list. The box T will point to the next list value that will be on the heap, rather than inside the const variant. The box T will point to the next list value that will be on the heap, rather than inside the const variant. Oh, so it's saying the box will point to the list on the heap. It's not going to point to the list inside the const variant. Conceptually, we'll still have a list created with list holding other lists, but this implementation is now more like placing the item next to one another rather than inside one another. Oh, so in the implementation, it feels like it's no longer like this. It's no longer the Russian dolls. It's girls side by side and holding hands. Side by side, side by side. We can change the definition of list enum, like those, and we need to put boxes. Box, new, oh my god. The amount of parentheses and trying to get them matched is not fun. Okay? Did I put a null into the box as well? Wait, hold on. What just happened? Did I put a null into the box too? I need to, because it needs to be a box. Yeah! Yeah! Now the Rust compiler likes it. Is there any possible way I can print this, big boy? The const variant will need the size of an integer plus the space to store the pointer data. The null variant has no values, so it needs less space than the const variant. We now know that any list value will take up a size of integer plus the size of a box pointer data. Any list value will take up the size of an integer plus the box. So either this size or this size, which is even less. So the variant of a list will be assigned this much size. By using a box, we have broken the infinite recursive chain. so the compiler can figure out the size it needs to store a list value. It looks like this. It looks like this. So it comes as an integer in a box. In a box. What makes pointer fat? The size of the point, the size? Boxes provide only the indirection and heap allocation. They don't have any other special capabilities, like those we'll see with other small pointer types. Okay, so they only provide indirection and heap allocation. They don't have any special capabilities. They don't have any performance overhead that these special capabilities incur. So they can be useful in cases like counts list, where the indirection is the only feature we need. The box T type is a smart pointer because it implements the derived trait, which allows box T values to be treated like references. When a box T value goes out of scope, the heap data that the box is pointing is cleaned up as well because of the drop trait implementation. So it's saying, I don't need to clean anything up. The box is going to clean up itself. A fat pointer is a pointer with metadata. Oh, we have encountered them before. I think there's a skinny pointer too. Is there a skinny pointer? Or it was just my imagination? Oh, they don't have skinny pointers. They're called same pointers. They're called same pointer. A same pointer is just a pointer, no additional data. And the fat pointer is the pointer with metadata. Oh, the jargons, the jargons. Okay, what do we have now? Treating small pointers like regular references with the derived trait. This reminds me of Decaf Cafe. What is that? Treating small pointers like regular references with the derived trait. Oh, we can dereference the pointer? The small pointer? Implementing the derived trait allows you to customize the behavior of the dereference pointer. You can customize it. You can customize how you dereference a pointer by implementing deref in such a way that the small pointers can be treated like a regular reference. You can write code that operates on references and use that code with small pointers too. Oh. Let's look at how the dereference pointer works with regular references. Then we will try to define a custom type that behaves like box T. And see why a dereference operator doesn't work like a reference in our newly defined type. We'll explore how implementing deref trait makes it possible for small pointers to work in ways similar to references. Then we will look at Rust's deref cohesion feature and how it lets us work with other references or small pointers. And we are going to build a my box, our custom box. And our box is not going to store data on the heap, but we are going to implement our own deref trait, I guess. Okay. Following the pointer to the value was the dereferenced pointer. Okay, so this is talking about the reference pointer. Let's write this down. We have a main function, and we have a x equals to 5, y equals a reference of x. And we assert equal x equals to 5. And we assert equal the value that y points to is 5. We set y equals to a reference to x. Y is a reference to x, and if we dereference it using the dereference star, how do we say it? It's star? We can access the value of x. I think that's what a pointer is. Yep. After dereferencing y, which is a reference of x, is equals to 5. Is equals to x value. And if we are comparing the reference to 5. Yep, you can compare. You can comparing a number and a reference because they are different types. So we need to have the star. Twinkle, twinkle, little star. Using the box T like a reference. We can rewrite the code to use a box T instead of a reference. Okay, so a box, new is the value of x. Oh, looks like it supports the reference. So would this work the same way? It does. We can use the dereference pointer to the box. And equals to 5 equals to x as well. And next we'll explore what is special about box T that enables us to use the dereference operator by defining our own box type. So we are going to define our own small pointer. And then look at how to add the ability to use the dereference operator. Let's define it. We have a struct myBox of type T. And we implement the new trait. Bye-bye! Amanda, thank you for coming. Good luck on your class. myBox x. So it's new, it returns a myBox of x. myBox with the value x. And if we use it, here is it got some squiggly lines here saying this cannot be dereferenced, probably because we didn't tell it how to dereference it. So we need to implement the dereference trait. The dereference trait. It requires us to implement one method named deref that borrows self and returns a reference to the inner data. So first import Oops. Deref. What is oops? All overloadable operators. Implement this trace allows you to overload certain operators. Oh, so we can implement. Implement the ref for my box E. Type target equals T. Target, what is target? It's a type. But why do we call it target? Function deref. It takes it borrows self. Target self.0. So this defines an associated type for derived trace to use. Associated types are a slightly different way of declaring a generic parameter, and we'll cover it more in chapter 19. Yeah, it's so secretive. It's so secretive. We fill in the body of the deref method with self.0. The deref returns a reference to the value we want to access with the stop point operator. The main function that calls the star on the myBoxT value now compiles an assertion parse. Why does self.0 gives you the X? You don't need to go through 15 seconds to catch up, my friend. All you need to do is just run a cargo new plus a name of the project, and then in the main function, just type in the code. This thing got all the code for you, and they have a GitHub page. You don't need to start from zero. You don't need to start from zero. You can just pick a chapter and just follow along. This is a problem for the future us. Future Cyan, the world is on you. The world is on you. What are my thoughts on Rust so far? It's fun. It's fun. It helps me to review a lot of concepts and learning a lot of other languages. It's like it got functional languages, it got some OOP, it got pointers, and it got a nice compiler. It's a language that makes me and other people happy. That's what I feel so far. So if you wanna learn it, go ahead. Go ahead. Welcome in, Jay. Hello. Okay, so we have the dereference pointer. Boom, boom. And now it's gonna say it's all good. It doesn't say it's all good, but there's no arrow, so it's all good. Because it knows how to dereference our box. It knows how to dereference our box. And on here, the reason the dereference method returns a reference to a value, and that the plain dereference outside the parentheses in here is still necessary. It's the ownership system. So when we do this, Rust actually did that. If the deref method returned the value directly instead of a reference to the value would be removed. It will be moved out of self. the value would be moved out of self. We don't want to take ownership of the inner value inside the mybox T. In this case, we use the dereference pointer. In most cases, we use the dereference point operator. So Rust automatically does this when we do this, because we don't want to take the ownership of Y. A new member, hello, thank you. Welcome to Neonstar. Welcome to Neonstar, thank you so much. Yes. Implicit deref cohesions with functions and methods. What is deref cohesion? What is this? Coercion? Why are you? Coercion. The practice of persuading someone to do something by force or threat. What? This is like forcing somebody to deref with force or threats. Rust is a very DOS language. It forces you to do a lot of stuff. Deref coercion is a convenience that Rust performs on arguments to functions and methods. Deref coercion works only on types that implement the deref trait. Deref coercion, am I reading it right? Converts such a type into a reference to another type. For example, deref coercion can convert big string to small string because big string implements the deref trait such that it returns the small string. It returns. Oh. So deref coercion works on types that implements the deref trait. Deref coercion converts such a type into a reference to another type, into a reference to another type. So say if we have this, and if we dereference it, it becomes this. Or we have a big string, and if we dereference it, it becomes this. If in the deref we set so. Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function, or a method that doesn't match the parameter type in the function or method definition. A sequence of calls to the deref method converts the type we provided into the type the parameter needs. Deref coercion was added to Rust so that programmers writing function and method calls don't need to add as many explicit references and dereferences with this and this, ampersand and star. The deref coercion feature also lets us write more code that can work for area references or smart pointers. To see deref coercion in action, finally an example! We can use the mybox we defined, as well as the implementation of deref that we added in here. Okay? So what's going on? We have a function, hello, and the name is a string slice. What does you do, baby? What does you do? Hello? It prints. we can call the hello function with a string slice as an argument. And the deref coercion makes it possible to call hello with a reference to a value of type myBoxString. So what are we doing? That m equals to myBox new string from Rust. And in the hello, we take the reference of m. What's going under the hood here? So m is an instance of myBox. And it has a big string of Rust. And then we pass the reference of it. Because we implemented a deref trait on myBox, Rust can turn the reference into this by calling deref. Okay, because target is big string, and calling this returns a reference of the big string. The standard library provides an implementation of deref on string that returns a string slice, and this is in the API documentation for deref. Rust calls deref again to turn the big string reference into string slice, which matches hello's function's definition. This is wild. This is loops and loops. I think what's happening is we put a big string in the arguments of myBox. And by calling deref, we turn the big string into the reference of the big string. And then, because the Rust calls the deref again, as mentioned in last chapter, it turned the reference to big string into the string slice. So you match the type of hello. This is wild. This is really wild. If Rust didn't implement deref coercion, we would have to write this code instead of that. Ooh, this looks ugly. So we don't need to do that. 回家路上，欢迎，路上小心。This dereference. Okay, what do we have? If Rust didn't implement the deref coercion, we need to dereference this into a big string, and then ampersand it, and then make a string slice to match the signature of hello. And yeah, this is hard to read, write, and understand for sure. 大家好 ，Deluxy 欢迎。Deref coercion allows Rust to handle these conversions for us automatically. Wow. Okay, now if I read again. Deref coercion converts a type into a reference to another type. Do we use it often? Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function or a method that doesn't match the parameter type in the function or method. So it feels like because we pass a reference to a big string to the hello, the Rust just does the pointer stuff for us, which I have no idea how this is implemented. A sequence of calls to the deref method converts the type we provided into the type the parameter needs. So this somehow converts into this. Magic. 太难了，怎么会这样？When a deref trait is defined for the types involved, Rust will analyze the types and use deref as many times as necessary to get a reference to match the parameter type. The number of times that deref needs to be inserted is resolved at compile time, so there's no runtime penalty for taking advantage of deref coercion. I do remember in C++ I wrote something like this. And here Ross is saying it will dereference for as many times we need to in order to match the function's signature. I kind of love Rust. I kind of love Rust. It just saves my headache. How deref coercion interacts with mutability, similar to how you use deref trait to override the stop operator on immutable references. You can use the deref mute trait to override the stop operator on mutable reference. What? Okay. When did we use the what is this? What is this? Give me an example. There's no example. When did we use deref trait to override the stop operator on immutable references? Was what we just done? Did we just do that? Okay, let me read on. So assuming we have done that, we can use the deref mute trait to override the stop operator on a mutable reference. So if we have mutable reference, we can use this to override that. Rust does deref coercion when you find types and trait implementation in 3 cases. Okay, so those are the conditions when Rust does deref coercion. First, from reference to T to reference to U, when T has this. You essentially did that, but with more syntactic sugar. I'm gonna get syntactic about diabetes. So this is the conditions where deref coercion happen. And this is when it is mutable, we use deref mute. From mute to an immutable was dereft. The first two cases are the same except for mutability. The first case states if you have a reference to T and T implements the deref to some type of U, we can get a reference to U transparently. The second case states that the same deref coercion happens for multiple references. The third case is trickier. Rust will also coerce a mutable reference to an immutable one, but the reverse is not possible. Immutable references will never coerce to multiple references. Because of the borrowing rules, if you have a multiple mutable reference, that mutable reference must be the only reference to that data. Otherwise, the program won't compile. Converting one mutable reference to one immutable reference will never break the borrowing rules. Converting an immutable reference to a mutable reference would require that the initial immutable reference is the only immutable reference to that data, but borrowing rules don't guarantee that. Therefore, Rust can make assumption that converting an immutable reference to a mutable reference is possible. So we learned about deref mute. We learned about deref coercion. And how to implement the deref trait. My brain is like flying naked in the sky. Treating small pointers like regular references with the deref trait. I'm not big brain. Gosh, I feel like it's going to take me another 1,000 years to understand. I think I understand the deref. The custom deref. Implementing the deref trait so it can be dereferenced. And the deref coercion feels like Rust is doing some work, so we don't need to dereferencing and referencing things over and over if there is some deref trait defined. Okay, I don't want to stuck here. Let's move on. So we have a deref. Now we can look at the drop trait. I don't know why I like the drop trait a lot. Maybe like as a cat, I just love to see things struggle and just die. So let's do it. Let's do it. The second trait important to the smart pointer is drop. Drop the beat, which lets you customize what happens when a value is about to go out of scope. You can provide an implementation of the drop trait on any type, and the code you specify can be used to release resources like files or network connections. What? What? So when something drops, you release some files and network connections? I would like to see how that works. It blows my mind. We're introducing drop in the context of small pointers because the functionality of the drop trait is almost always used when implementing a small pointer. For example, when a box T is dropped, it will deallocate the space on the heap that box points to. In some languages, the programmer must code to free memory or resources every time they finish using an instance of a small pointer. If they forget, the system might become overloaded and crash. In Rust, you can specify that a particular bit of code can be run whenever a value goes out of scope. And the compiler will insert this code automatically. Okay. Yes, that was a brain phrase, but I understand it. So when some value goes out of scope, we can insert some code at that moment. As a result, you don't need to be careful about placing cleanup code everywhere. And you still won't leak resources. Amazing! Drop trays are like destructors. Yes. Good stuff. Specify the code to run when a value goes out of scope by implementing the drop trait. The drop trait requires you to implement one method named drop that takes a mutable reference to self. To see when Rust calls drop, let's implement drop with printline statement for now. What? Oh. So what do we have? Rust not leaking resources. Exactly. Rust never leaks. Unless it's unsafe, right? Struct custom smart pointer. We have a struct of that's called custom smart pointer, and then it got us data of string, and when we implement the drop trait for custom smart pointer. No. Custom smart pointer. And we have a drop function that takes a mutable of self. What do you do? And then we print line. And when the thing drops, we said dropping. Dropping data. Can I just do self.data like this? I don't think it works. Hey. Self.data. Hey, so when it dies, it's going to say dropping data, and the data is gonna show up. Function main. Let's see, equals to custom pointer of data. This feels like JSON. String from my stuff. I'm gonna jump my stuff. I keep thinking of Rust on metal. Wait, is Rust kind of related to metal? I can't leave it empty? Oh yeah, not Rust was named after a fungus. I remember. Hello Roger, welcome. So what am I currently writing? I'm trying to understand and drop how to customly do something when a value is dropped. Okay, so we have a custom one, the first custom pointer. Hello. And the second custom pointer that says other stuff. And then finally print line. Custom smart pointers created. Okay. But it's not going to call a drop function, right? Like this does nothing. Wait, no. At the end of the main, does it call drop and it will say dropping data? Let's see. Reload! It created the data. And after the main, it dropped like a stack. It dropped the other stuff first and then dropped my stuff. What? The drop tray is included in the preload, so we don't need to bring it to scope. We implement the drop trait here and provide an implementation for the drop method. Oh, this is the trait. This is the method. This is the method. That calls the print line and shows the data. The body of the drop function is where you would place any logic you wanted to run when an instance of your type goes out of scope. We're printing some text here to demonstrate Rust will code drop. Yeah, Rust code the drop. Variables are dropped in the reverse order of the creation, so D was dropped before C. Okay, that's how the drop works. And we can drop our value early. We can drop our value early if we hate them or we just ditch them. Unfortunately, it's not straightforward to disable the automatic drop functionality. Disabling drop isn't usually necessary. The whole point of the drop trait is that it is taken care of automatically. Occasionally, however, you might want to clean up a value early. One example is when using smart pointers that manage locks. You might want to force the drop method that releases the lock so the other code in the same scope can acquire the lock. Oh, we're preparing for concurrency. We're preparing for concurrency. It's gonna be fun. Rust doesn't let you call the drop trace drop method manually. Instead, you have to call the standalone stdmem drop function provided by the standard library if you want to force a value to be dropped before the end of the scope. If we try to call the drop method manually, it's not gonna happen. So if we wanna drop, we just call the method, it's not gonna happen. What would it say? It will say, explicit destructor calls not allowed. Help! Consider using drop function. Yep, we cannot call the drop explicitly. Rust doesn't let us call drop explicitly because Rust will still automatically call drop on the value that's at the end of the main. This will double free arrow. This will be a double free arrow because Rust will be trying to clean up the same value twice. Oh, that would be dangerous. That would be dangerous. That's why it doesn't want us to just call it, because Rust might do it again. But what we can do is we can just... Can you believe it? It's in the standard library, so if we just drop, we can drop it early. I just like drop school, drop VTubing, drop mic. I'm creative. Is it just a move? What kind of move? Drop school. The text. Okay. Oh, I think I'm a master of drop. I'm a drop master. Dun dun. There should be like some shining text around my head. It says drop master. I have mastered the art of dropping. You can use code specifying your drop trace to make a cleanup convenient and safe. With the job trace and Rust ownership system, you don't have to remember to clean up because Rust does it automatically. It's basically saying Rust does everything. The ownership system makes sure things are always valid. And boom, thanks Rust mommy. Thanks Rust mommy. Job scoop keeps learning anyways. We're the next Bill Gates. Let's go. Cyan job to beep. Oh, Cyan the job master. It moved the variable into the function and dropped it when the function ends. For the drop function? For this? Oh. We move it to a function and then drop it when it ends. Oh, I didn't know it's like that internally. I heard it once, and now it kind of reminds me. Okay. Now we have examined the box T and some of the characteristics of the smart pointers. Let's look at a few other smart pointers defined in the standard library. You can try to write your own drop function, which is a function that takes a value and just ends. Yeah? 1小时前1加1等于2，什么呀？什么呀？已经 Chapter 15了。We're not doing 1 plus 1 equals to 2. If we're doing that, we're doing the proof of it. They're very scoy. Okay, just kidding. Oh, we're at the reference counted smart pointer. We're counting reference. And we'll have reference cell and the reference cycle can link memory later. Okay. We are counting reference. Yeah, we are counting reference. In the majority of cases, ownership is clear. Okay? Oh, but there are cases when a single value might have multiple owners. In a graph data structure, multiple edges might point to the same node, and that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned unless it doesn't have any edges pointing to it. So, in Rust, if you want to do a graph data structure, you gotta use the reference counted smart pointer. Soka. Welcome, Richard. Hello, V50. Hello, V50. 欢迎. To enable multiple ownership, Rust has a type called reference counted, which is a abbreviation for reference counting. Okay, it keeps track of number of references to a value to determine whether or not the value is still in use. If there are 0 references to a value, the value can be cleaned up without any references being invalid. Oh, I like this analogy. So reference counting is a TV in a family room. When a person enters to watch TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn off the TV because no longer anyone is watching. But if somebody turns off the TV while others are still watching, there will be an uproar from the remaining TV watchers. So there is a counter that counts how many people are watching, and when there are 0 people watching, we are throwing the TV away. Is that? Are we throwing the TV away if there's 0 people watching? Damn! That's violent. That's violent. But this is reality of Rust. We're throwing the TV away. If we use the cross-counting type when we want to allocate some data on a heap for multiple parts of our program to read, and we can determine at compile time which part will finish using the data last. What the heck is a long sentence? Oh, so we use reference counting. If you want to allocate some data on a heap for multiple parts of our program. What? We can determine at compile time which part will finish using the data last. So we have a program that has multiple parts that read some data, and when that happens, we can use the reference count. Monitor can rest up. Oh gosh, I don't have a TV. I just buy a new TV every time I watch something. Yeah, you're rich. I'm rich. If we knew which part would finish last, we could just make that part's data's owner, and the normal ownership rules enforced at the compile time will take effect. Oh, so reference counter is when we can determine which part will use the data last. If we can know which part will finish last, we can just make that part the data's owner. Note that reference counting is for use in single-threaded scenario. Okay, no multi-threaded yet. Not yet. Ooh, what is this? This is a cons list with 2 hats. It's a 2-hat snake. Using reference counting to share data. Let's return to our cons list example, okay? Recall that we define it using box T. This time, we'll create 2 lists that both share the ownership of a third list. Conceptually, this looks like this. We create a list A that contains 5, 10. And then we have B with 3 and C with 4. Can you guys even see it? It's so tiny. The graph doesn't become bigger. Okay. Morning, welcome. It's a crab crawl. It's a crab crawl. That's such a nice analogy. Crab. Trying to implement this scenario using our definition of a list with box T won't work. Nutty. Why does it not work? So this was our previous implementation. Box list. And no. Use create list cons no. Function main A equals to cons 5 box new cons 10 box new meow. Okay, we have an A. Hello, Clara! Welcome! At B equals to cons 3 box new A. And let's C equals to cons 4 box new A. And it's saying no, it doesn't work. It doesn't work because we're using A twice. The value was moved here, what is used again after the move? So how do we resolve it? How do we resolve it? We can use the reference counter. But instead of the box, I'll change it into reference counter. Reference counter. Use std reference counter. And we change it into reference counter. It still has some problem. We need to clone it. Clone the reference of A. The implementation of clone doesn't make a deep copy of all the data, like most types of implementation of clone do. It only increments the reference count, which doesn't take much time. Deep copies of data can take a lot of time. By calling clone for reference counting, we can visually distinguish between the deep copy kind of clone and the kinds of clone that increase the reference count. When looking for performance problems in the code, we only need to consider deep copy clones and disregard close to shallow copies. So we are saying we would like to use this. So it shows that we are not using the deep copies. Clone. My chat is dead. Okay, it's not dead. It's not dead. Alright. あれ？どうしました？ The outer layer is also counts. New. Dormant chat. Oh, I saw an ad and I cleaned it up. Oh. And then the chat just dies. Like my page on my side, I can't see any chat if I remove something. If I block something. Oh. Oh, so. Okay. Let's run it. And it has no problem. No problem. Except for the warning, which doesn't matter. But if you want to use a variable multiple times, we can use the reference counting. Reference counting is useful if data is expensive to compute and only need to compute once. Then you send the data somewhere else and you do not expect to use the data ever again. Responsibility move outside of yours. So the egg only needs to compute once if we use the reference pointer. Reference counting, my point. Nice. Cloning a reference counter increase the reference count. Is there any way to see the reference count? I can see the reference count. It might have other uses, but I use it mostly like that. Oh, thank you, CrowFX. And it looks like it's nice thing to do to reduce performance. To reduce performance overhead. To calculate less. Okay, so what do we have now? What do we have now? So here we have reference counter of this very nested counts list. Count after creating a. Yeah, print number of times it's used. And here it's being used once. I would very much like to know what would be the numbers. 睡着了没关系，可以接着睡啊。不许失眠。Count after creating a equals to 1. Oh, so after creating a equals to 1, the reference counter is already 1. Count after creating 2 is 2. And inside this tiny scope, count after creating C still adds to 2, so equals to 3. And after C goes out of scope, it just reduces. Lexi, hello! Let's skip this chapter because you got so confused by it. I watched the video by Let's Get Rusty. It is so freaking good. It explains the things very clearly and it follows this book very nicely. So yeah, that helped me a lot. The winning point is the reference counting clone feature. It is cheaper to clone pointer and not a huge amount of vector or hash map. It clones the pointer, not the actual content. Is that why Rust is kind of fast? So many performance optimizations. Referencing counting is an easy concept once you know how it works. Do we use it a lot? I feel like with something that computes a lot and using the clones of it comes pretty handy. The best way to understand ref cell, reference counting is to implement them yourself. That's what the one video I watched did. It was incredibly useful and made me feel smart. Oh, that sounds cool. I'm going to take a note and maybe do it. Implement Rust functions yourself. At each point in the program where the reference count changes, we print the count. Okay. It's strong count rather than count because it also has weak count. It has a weak count. And A has an initial value of 1. And each time we call clone, the count goes up by 1. And C goes out of scope, the count goes down. It just does it by itself. And when B and A goes out of scope at the end of the main, the count becomes 0. While immutable references Reference counting allows you to share data between multiple parts of your program for reading only. If a reference counting allowed you to have multiple references too, you might violate the borrowing rules. Multiple mutable borrows to the same place can cause data races and inconsistencies. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and ref cell type that you can use in conjunction with reference counting to work with this immutability restriction. I'm afraid of mutability. The motivating use of reference counting is now very strong. It's useful if you're using async but not multi-threaded, because for single thread you usually just rely on borrow check. Ooh. Reference counting is confusing because its feature overlaps with the default borrow feature of Rust. And rough cell. Now it matches mutability with references. Can we handle this? I'm scared. Ref cell and interior mutability pattern. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Oh, I think the introduction talks about it, and I was like, how is that possible? Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside the data structure. To bend Rust's usual rules that govern mutation and borrowing, we haven't yet covered unsafe code, and we will later. We can use types that use the interior mutability pattern when we can ensure that the borrowing rules will be followed at runtime. Even though the compiler can't guarantee that, the unsafe code involved is then unwrapped in a safe API, and the outer type is still immutable. Thank you. Bye, Wixie. Thank you for coming. Oh, reference counting can be used to graph. Nice. Nice. The edges. The node. Okay. Ref cell. Let's go. Let's go. Enforcing borrowing rules at runtime with ref cell. Unlike ref counting, the ref cell type represents single ownership over the data it holds. It represents single ownership. Okay. So what makes ref cell different from a type like box T? Recall the borrowing rules you learned in chapter 4. Okay, so what's the difference between ref cell and box T? At any given time, you can have either, but not both of, one mutable reference or any number of immutable references. References must always be valid. At any given time, you can have either one mutable reference or any number of immutable reference. So you can only have one mutable reference or any number of immutable reference. It doesn't matter how many immutable references you have. You can only have one and only mutable reference. And references must be valid. With references and box T, the borrowing rules invariants are enforced at compile time. With ref cell T, these variants are enforced at runtime. Okay, so box T, the rules are enforced at compile time. And with reference cell, the variants are enforced at runtime. And my cat is here. Hello. You wanna learn ref cell? You wanna learn how to be unsafe? My cat is super interested. My cats are super interested in that. It is not hungry. I fed him 2 times already. It's just lonely. And missing being destructive. Stop. Let me grab him. Okay, you're a good boy. Sit down, me. Don't move. Kiranas! Welcome, hello. What were we talking about? We were talking about ref cell. This invariance of enforced at runtime. And box is enforced at compile time. With references, if you break these rules, you'll get a compiler error. With ref cell, if you break these rules, the program will panic and exit. The advantage of checking the borrowing rules at compile time are the errors that will be caught sooner in the development process. And there's no impact on runtime performance. For those reasons, checking the borrowing rules at compile time is the best choice. The advantage of checking the borrowing rules at runtime is that certain memory safe scenarios are then allowed, whereas they are disallowed by compiler time check. Static analysis like Rust compiler is inherently conservative. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting program. The halting problem, which is beyond the scope of this book. What is the halting problem? Is that a turning machine? Halting problem. It's a decision program about properties of computer program on a fixed turning complete model of computation. All program. What? I think I said turning machine. All program can be written in some given programming language that is general enough to be equivalent of a Turing machine. Programs can tell if other program will eventually stop or go into an infinite loop. Will this program ever stop? Cat engaging unsafe behavior. Yes, he's a master of unsafe behavior. Halting problem is, will this program ever stop? Oh. Oh, I remember a bit of discrete math. It's coming back to me. Okay, that was my curiosity. Let's move on. Because some analysis is impossible, if Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program. In this way, it's conservative. If Rust accepts an incorrect program, user wouldn't be able to trust the guarantees Rust makes. However, if Rust rejects a correct program, the programmer will be inconvenient. Okay, that's obvious. The rough cell type is useful when you are sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. Similar to reference counting, reference cell is only for use in single-threaded scenario and will give you compile time and error if you try to use it in multi-threaded syntax. Am I even reading it right? Is it like a reference cell? Ref cell? A mutable memory location will dynamically check the borrow. Why is it cell? What is a cell? Have I learned any informal communication in computer science? Yes. I took some university courses. I have. And forgot half of it after paying thousands of tuition. And still having fun learning Rust. Because the university doesn't teach Rust. At least in my university. Here is a recap of the reasons to choose box, reference counting, or ref cell. Reference counting enables multiple owners of the same data. Box and reference cell has single owners. Okay, so this reference counting has multiple owners of the same data. The others have single owners. The others are loyal. The reference counting isn't loyal. Box state allows immutable or mutable borrows check at the compile time. Reference counting allows only mutable borrows check at compile time. Reference cell allows immutable or mutable borrow at the runtime. Okay? Because ref cell allows mutable borrows check at the runtime, you can mutate the value inside it, even it is immutable. Okay, I think this is a recap. This is a review. Mutating the value inside an immutable value is the interior mutability pattern. Okay, we'll learn about it. Cyan, what do you think of university? I never went, so I don't know how it works. How do I think of university? That's a good question. It helps you to... it helps you to get a job. It teaches some basic stuff. And besides the knowledge, you make a lot of friends and have like amazing experience with it. But just I don't know if I'm experienced to say this. I do feel those who are already really good at coding, they don't need university classes, then they can just apply for a job. I heard like companies like Google, if you have their skill set, it doesn't really matter if you have a degree or not. But some other company does care about like GPA and stuff. But I really feel a lot of learning occurs outside of the university. And I heard like after a few years, your education doesn't matter that much. I think I should join some university club despite not going. That would be great. Get some friends and network. Yeah, not just friends. You can, have some like romantic experience in your university. It's a place for our young people. To experience life and parties. So those are something that's pretty unique. But about education, I feel like most of the learning occurs outside of the classes. Thank you, Mitama. I still think it gives good programming experience though. I was good at programming before university, but university had made me many times better at programming. Yes, that happens. That happens too. Like those are already good at programming. If you guys sincerely wanna learn more, you can use all the resources in the university. Like go to TA hours, go argue with professor on what's the best ways to do stuff, and see and network with people who are like-minded. It's going to make you really, really good in that aspect. My university is online with no social interaction, so no socialize. Is there a group you can join? I really wish like things can go to quote unquote normal, more face to face, you know? Do you like to meet like-minded people? Go ahead. Go ahead. I don't know many programmers in real life. I feel like all my friends are programmers. That kind of like limits my world too. Okay, interior mutability. A mutable borrow to an immutable value. What is that? What is that? Programmer Papa, I know. I know. What do we have here? Ooh, the main function. At x equals to 5. At y equals to a mutable reference of x. And no, it's not okay. Why is it not okay? Because x is not mutable. Code outside of the values method would not be able to mutate the value. But if you use refcell, you can get interior mutability. But refcell doesn't get around the borrowing rules completely. The borrow checker in the compiler allows this interior mutability. And the borrowing rules are checked at the runtime instead. If you violate the rules, you will get a penalty. Okay, so how do we use refcell? Mock object. A test double is the general programming concept for a type used in place of another type during testing. Mock objects are specific types of test doubles that record what happens during a test, so you can assert that the correct action took place. Rust doesn't have object in the same sense as other languages have object, and Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purpose as a mock object. Here is the scenario we'll test. We'll create a library that tracks a value against a maximum value and sends message based on how close to the maximum value the current value is. This library could be used to keep track of users' quota for the number of API calls they're allowed to make, for example. Our library will only provide the functionality of tracking how close to maximum a value is and what messages should be at what times. Applications that use our library will be expected to provide a mechanism for sending the messages. The application could put a message in the application, sending an email, send a text message, or something else. The library doesn't need to know the detail. All it needs is something that implements a trait will provide called messenger. Oh, it's a long one. It's a long one. Online universities seem kind of hard to keep up with. I think I had a semester online. They reduced the course load because like it was COVID. But like yeah, seeing TAs is like much harder. Seeing the groups is much harder. Communication is much harder. And it's less motivating to go interact with the instructor. I do like face-to-face, but you get more free time if it's online. Pointers are paying. Yes, Gula honey, welcome. Welcome to the bank. Welcome to the bank. Online has been hard, needing pure self-motivation. Yes, it's hard. It's hard. I really miss face-to-face. I wanna go to office someday. Okay, so we have a new file, library.rust. Library. And what do we have? We're making a library of public trait, messenger, function send, self, message, a string slice. And public struct limit tracker. Limit tracker has a TKI time lifetime and messenger. Messenger, a reference of type T, value max. Wow, this is long. What do we have? We have a trait. It has a send. And my cat is here. Hello. You're here again. You're here again. And we have a struct of limit tracker that has a message. Messenger. We have messenger, value, and max. Whew. And we implement lifetime T. A limit tracker. Messenger. Public function new. Messenger. Max. It returns a new limit tracker. There's a limit tracker. We initialize it. Value is 0 and max. And there's a set value. Public function set value. Build self value. Right. What am I writing? So we can set a value of a limit tracker, I guess. self.value equals to value. Let percentage of max equals to self.value as f64 divide by self.max as f64. Yeah, as f64. If percentage of max is larger equals to 1.0, self.messenger.send. Else if percentage is larger than equals to 0.9, self.messenger send almost. And else if percentage larger than equals to 0.75, self.messenger send 75%. I don't want to write an entire sentence. It's so long. It's so long. Science controls bus is broken. Why? Why? I feel like I have to type the entire thing to understand it, and I think I have a better idea of what it is. Oh, what is a UCZ? UCZ. Come on. Yosh. Okay. We have those. Oh, a cattail. Cattail. Stop. Stop. Stop robbing me. No. Okay. What do you got to say about this code? One important part of this code is the messenger trait that has one method called send that takes immutable reference to self and text of the message. This trait is the interface our mock object needs to implement, so the mock can be used in the same way a real object is. The other important part is that we want to test the behavior of setValue method on limit tracker. What? Limit tracker? Oh, on the limit tracker, we set the value. We set the value. Yes, we can change what we pass for the value, but set value doesn't retain anything for us to make assertion on. We want to be able to say if we create a limit tracker with something that implements the messenger trait and a particular value for max. When we pass different numbers for value, the messenger is told to send appropriate messages. Okay. We need a mock object that, instead of sending an email or text when we call send, will only keep track of the messages it's told to send. We can create a new instance of the mock object called create a limit tracker that uses the mock object. Call the setValue method on limit tracker and then check that the mock object has the messages we expect.也还在播，也想把这一个 chapter 播完，也要战胜指针。One of these days, you are going to need to show us your cat. My cat is everywhere. Everybody has my cat. My cat is black. It's a black cat. You also typed out the entire code. I wish I could improve on how I read the code. Oh gosh, this is so long. What the heck? Okay, I'll stop testing. I'll stop typing. It's too much. What do we have? We have a test, okay. And there's a send message. And we have a monk messenger that returns monk messenger that has the send message in a vector. Implement messenger for monk messenger. Our monk messenger what? We have a monk messenger and we have a multiple limit tracker for the monk messenger, and the max is 100. And then when we set the limit tracker value equals to 80, so the messenger will have value of 80. This is so long. Okay, so our messenger have a value of 80 and then prints a warning. And we're testing that it is indeed printing the warning. Are we? Are we? Monk messenger sent messages length equals to 1. Welcome for derivative, hello. 是妍妍，妍妍有什么好战胜的？妍妍是用来呵护的。Okay, just kidding. What is this? This task goes define a monk messenger. A monk messenger, okay? A monk messenger, a monk messenger. That has a sent messages field with a vector of string to keep track of the messages it's told to send. We also define an associated function new to make it convenient to create new monk messenger values that start with an empty list of messages. Stop rubbing the microphone. What else? We then implement the messenger trait for monk messages so we can give monk messenger up to a limit tracker. We implement the messenger trait for the monk messenger. Okay, for the monk messenger, so we can give it to we can give the monk messenger to limit tracker. The limit tracker. In the definition of the send method, we take the message passed in as a parameter and push them into send messages. There's a subscriber. Welcome to Neonstar. I don't hear that. Why do I not hear that? I need to have the monitor. I never hear that. Welcome to Neonstar. Thank you. It sounds like somebody opened a chest. I think I customized it a long time ago. I don't remember what it sounds like. Can somebody remind me? It's like no. It's definitely there. Okay. I had no idea. Okay, what does this test do? When limit tracker sets value to 80, We create a new mock messenger. Which will start with empty list of messages. Then we create a new limit tracker and give a reference to mock messages and give it to a max value of 100. We call set value to 80s. Then we assert that the list of messages the mock messenger is keeping track of should now have a one message in it. And there's one problem with this test, which is here. Why is that a problem? Why is that a problem? It says cannot borrow as mutable. Wait, what? Oh, wait. This is not in the right package. Okay, right here. Right here. We have a send, and the saying self is a reference. So data it refers to cannot be borrowed as mutable. Self does send messages. So I cannot do mutable here by pushing. So what do I do? We use the ref cell. So in the mock messenger, we use ref cell. Ref cell. Okay. So now what? I can push already? Okay, so first we need to import it when you use it. Cell ref cell. Welcome, Jasina. Hello. And send message is also a ref cell. And the push, we need to have a borrow mute push. Here, new. Okay, what's going on? The send message field is now of type ref cell whack string instead of whack string. In the new function, we create a new ref cell whack string instance and run the empty vector. For the implementation of the send method, the first parameter is still an immutable borrow of self, which matches the trait definition. We call borrow mute on the ref cell vector string. The borrow mute on the send messages, which matches the trait definition. Wait, what? Which is the vector? Then we call the push on a mutable reference to the vector, keep track of the message during the test. The last change we have to make is the assertion to see how many items are in the inner vector. We can borrow on the ref cell vec string to get an immutable reference to the vector. Now that you have seen how to use ref cell, Let's dig in how it works. What? Wait. I need to borrow it. And if we roll it now, oh, I need to do cargo test. About empty. If this is empty. Okay, this is okay, it passed. It passed after we use a bunch of borrows with the ref cell. Keeping track of borrows at runtime with ref cell. When creating immutable and mutable references, we use the ampersand and the mute reference and reference mute syntax. With ref cell, we use the borrow and borrow mute methods, which are part of the save API that belongs to ref cell. The borrow method returns the small pointer type ref, and the borrow mute returns the small pointer type ref mute. Both types implement deref, so we can treat them like regular references. The ref cell keeps track of how many ref and ref mute small pointers are currently the ref cell keeps track of how many ref and ref mute small pointers are currently active. Every time we call borrow, the ref cell increases its count of how many immutable borrow are active. When ref value goes out of scope, the count of immutable borrows goes down by 1. Just like the compile time borrowing rules, ref cell let us have many immutable borrows or 1 mutable borrow at any point of time. Thank you, Adam. Have a good night. Have a good night. Thank you for coming. The ref cell keeps track of how many reference. But this keeps track of how many reference and reference mutable small pointers are active. Oh, so we still keep the rules. We still have many immutable borrows or 1 mutable borrow at any point of time. The only thing ref cell does is let the compiler not to check it, and only panic if the rules are broken. If we try to violate these rules rather than getting a compiler error, the implementation of ref cell will panic at runtime. Oh. Okay. And what is this? Messenger from work messenger. Send. Let mute 1 borrow equals to. Also, when there are 2 mutable borrow, it's not gonna be happy. The test will fail because we can only have 1 mutable borrow at any point of time. Catching borrowing errors at runtime rather than compile time means that you would find a mistake in your code later in the development process, and possibly not until your code was deployed into production. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. However, using ref cell makes it possible to write a mock object that can modify itself to keep track of the messages it has been seen while you're using it in a context where only immutable values are allowed. We can use ref cell despite its trade-off to get more functionality than regular reference provide. Okay. One day when I write test double in Rust, Hope I remember it. Having multiple owners of immutable data by combining reference counting and reference cell. A common way to use reference cell is in combination with reference counting. Recall that reference counting lets you have multiple owners of some data, but only gives immutable access to that data. But it only gives immutable access to that data. If you have a reference counting that holds a reference cell, you can get a value that can have multiple owners and that you can mutate. For example, recall the counts list, where we use reference counting to allow multiple lists to share ownership of another list. Because reference counting holds only immutable values, we can't change any of the values in the list once we have created them. Okay? So if we use reference counting, it's all immutable and we can't change the value. But if we use reference cell, then we can change the value. What does this do? Mamma mia! Here we go again. We have a list. Oh, the integer is the reference cell? And that has a reference counter? What? You love that song. Is that from a musical? Mamma mia! I have never watched it. Value equals to reference counter, reference cell. We have a bunch of reference counter, and we have a B that has A, and we have a C that has A. We create a value that is an instance of reference counter, reference cell I32, and store it in a value, in a variable named value, so we can access it directly later. Then we create a list in A with a const variant that holds value. We create a list in A with a const variant that holds the value. Oh, so here the const variant holds the value. When you clone the value, both A and value has ownership of inner 5. Rather than transferring the ownership from value to A, or having A to borrow from value. So both value and A have ownership of 5. We wrap the list in a reference counter, so when we create list B and C, they can both reverse to A. After we create a list in A, B, and C, we add a 10 to the value in value. We do this by calling borrow mute on value, which uses the automatic dereferencing feature we discussed in chapter 5. To dereference the reference counting to the inner reference cell value. And if we run it... No. Wait, hold on. Let's move this. Into the main. Okay. And cargo run. And we have 15. We all have the modified value of 15. By using reference cell T, we have an outwardly immutable list value. But we can use the methods on reference cell T that provides access to its interior mutability, so we can multiply our data when we need to. The runtime checks of borrowing rules protect us from data races, and is sometimes worth trading a bit of speed for this flexibility in our data structures. The standard library has other types that provide interior mutability, such as cell_t, which is similar except that instead of giving reference to the inner value, the value is copied in and out of the cell_t. There's also mutex_t, which offers interior mutability that's safe to use across threads. We'll also discuss its use in chapter 16. Okay, there's so many stuff! It's easier to learn multi-threaded, and its sync concept Rust. Its sync concept than this. I hope multi-threaded will be easier. I feel like the mutex will be used in multi-threaded to unlock the threads. Thank you, CrowFX. Welcome back, Song388, to answer your question. Music came first, and then the music was adopted in stage play. What? It was the music came first, and then there was the stage play of Mamma Mia? What? I thought it was the music in the musical. I never knew the egg is actually the music, and then born the chicken of the musical. What? Oh, it's recursion, guys. It's recursion. It's recursion. Okay. Last bit of this. Reference cycles can leak memory. The most I was able to comprehend was being able to do cargo run so far. Everything start and end with cargo run. I feel like this is one of the hardest chapters in this entire book. It is. I feel like I need to watch some video on this to review. And I will forget. Unless I have to use it sometime. Okay. Last one! The last one. Reference cycles can leak memory. Rust memory safety guarantees make it difficult, but not impossible, to accidentally create memory that's never cleaned up. Preventing memory leaks entirely is not one of Rust's guarantees, in the same way that disallowing data races at compile time is. Many memory leaks are memory safe in Rust. Memory leaks are memory safe in Rust? What? Is memory leak safe? We can see that Rust allows memory leaks by reference coding and reference cell. It's possible to create references where items refers to each other in a cycle. This creates memory leaks because the reference count of each item in the cycle will never reach 0, and the values and the values will never be dropped. It is saying that memory leaks is possible in Rust. Rust borrow checker and types it has created to get around it are arguably the hardest thing about the language. They created a cage and invented a window. I think it's okay to not be able to comprehend reference counting and reference cell now. I think it's useful for creating crates, but not for end user. Okay. I feel like I understand the high level of it, but not sure when I will seriously need to use it. Memory leaks are possible in Rust. Let's see, let's create memory leaks. Let's have fun. Let's leak people's memory. Creating a reference cycle. Let's look at how a reference cycle might happen and how to prevent it, starting with the definition of the list enum in the tell method. Okay? We have a main. We have a main of a list. Yes, we have a main of a list. I feel like I'm half sleepy. No. I can sleep and call, yo. That's totally doable. All this info is gonna leak from my memory. Have the Rust compiler built in your brain. And ask the reference not to cycle. Then you won't have memory leak, hopefully. Okay, so we have a list. And the list has a associated function tail, which is an option of reference cell of reference copy of list. And self can be null. What? Null and none are different stuff. Oh. Okay. And cuts is some item. What are we doing here? The second element in the const variant is this big guy. It's this big guy. Instead of having the ability to modify the i32 value, we want to modify which list value. We want to multiply which list value a const variant is pointing to. We want to modify the list value. We are also adding a tail method to make it convenient for us to access the second item if we have a const variant. So we're accessing the second item of const variant. I forgot to free the box dynamic nickel from your memory. The cats are trapped. No, animal abuse. Okay. And here we have a main function. Mamma mia. I think my control A is broken. Or is it because my Vim? I can't really select all. What? This is weird. I think it's because of my whim. Anyways, what do we have here? What do we have here? Memory safety and memory leaks are different. Memory leaks can happen in mem-safe languages because they are built to leak tolerant. Memory unsafe can cause any number of issues from data corruption to exploits. What? So, you can leak memory and still be safe? Memory leaks are memory safe? So this is what it means. Oh. Memory leaks might, at worst, cause denial of service, which can be exploited or unintentional. When they did those, is that what they do? No. DDoS is like sending a lot of requests. Okay. What do we have in the main function? Memory leaks just mean you don't have a pointer to that memory anymore, so it takes up space. But you don't know... you don't know where it is. Oh. Those is anything that takes down a service. Oh. So if like we have so many memory leaks, our memory has explosion, boom, use up the memory. Then we'll have a 503. Memory leaks are performance issue. If you have them, your program uses more memory because it can access some piece of memory that wasn't freed. Safety is dealing with program correctness. Oh, safety is dealing with program correctness. So it's okay to stay safe and leak, because leak is only with performance issue. DDoS is a distributed attack that floods a server with requests from multiple attackers in a network and uses up all of its memory in processing. Oh. Yes. Is this those related to memory leak at all? Also, preventing memory leaks will be very difficult due to a number of reasons. Human reason? Dong. Okay, coming back to the main function. We have a reference counting instance holding a list of value. A list value in the variable A. With an initial list of 5 and null. We then create a reference counting instance holding another list that has 10 and points to the list in A. Let's just run this. What does it say? I feel like the messages are more important. Okay, so initially we have a reference counting of 1. And then if we access a.tail, it will be null. And let's create B. And B has a pointer to A. So the reference count after B's creation is 2. The reference count of A after B's creation is 2, and reference count of B is 1. And the tail of B is A. If let sum link equals to a.tail. So this chunk dot borrow mute equals to B. To change the value inside from an reference and counting list that holds a null value to the reference counting list in B, you use the borrow mute method to change the value inside from a reference list that holds a null value. Oh. So we change a null value. Wait. The tail of A is null, and we are changing it to B. And that increment the reference count of A. Okay, it's somehow making sense. Woo! Memory leaks can be caused by DDoS. Yes, through memory value exhaustion or memory resource exhaustion. Nice. I never saw you can DDoS with memory leak. But thinking about it, yes, it exhausts the memory resource, just like sending a lot of requests. Ooh! Oh, there's circles. There's circles of circles and circles. Wait, what's going on? The reference count in both A and B are 2. At the end of main, Rust drops the value B, which decreases the reference count of This intense memory can be dropped either. So it's like A initially refers to 5, and B refers to 10, and then what? A reference cycle lists A and B pointing to each other. At the end of the main, Rust dropped variable B, which decreased the reference count of reference counting instance from 2 to 1. The memory that reference counting has on the heap won't be dropped at this point because its reference count is 1, not 0. Then Rust drops A, which decreases the reference count on the A reference list to from 2 to 1 as well. The instance memory can be dropped either because the other reference list instance still refer to it. The memory allocated to the list will remain uncollected forever. If you uncomment the last print and run the program, Rust will try to print this cycle with A pointing to B pointing to A and so forth until it overflows the stack. What? It can overflow? So if I uncomment this, A next item. It's stack overflowed! It's stack overflowed! Yeah. We made something big, guys. We stack overflowed. It points things at each other and they keep pointing to each other and it overflows the stack. Creating reference cycle is not easily done, but it's not impossible either. If you have reference cell values that contains reference quantity values or similar nested combination of types with interior mutability and reference counting, you must ensure that you don't create cycles. You can't rely on Rust to catch them. Creating a reference cycle will be logic bug in a program that you should use automated tests, code reviews, and other software development practice to minimize. I don't know if there's a single language that can prevent a stack overflow. Scratch? I'm just kidding. Well, I can't believe they made Stack Overflow website into a real thing. I think when the Stack Overflow is done, it has some like interesting page showing. When the service is done, it will say like Stack Overflow or something. The Stack overflowed. Another solution for avoiding reference cycles is reorganizing your data structure so some references express ownership and some references don't. As a result, you can have cycles made up of some ownership relationships and some non-ownership relationships, and only the ownership relationship affect whether or not a value can be dropped. Oh. What is a weak T? My mind is so twisted. How much more do we have? How much more do we have? A bit. Cyan, you sign up for this. Let's go. What is a weak T? Is there a strong T? The clone increased the number of strong counts of reference and counting, and reference and counting instance is only clean up if its strong count is 0. You can also create a weak reference to the value within with a reference counting instance by calling reference counting downgrade and passing a reference to reference counting key. When you call reference counting downgrade, you get a small pointer of type weak instead of increasing the strong count. It increased the weak count, so it does have a weak count. I use the weak count to keep track of how many weak references exist. The difference is weak count doesn't need to be 0 for the referencing counting instance to be cleaned up. Strong references are how you can share ownership of a reference counting instance. Weak references don't express an ownership relationship. They won't cause a reference cycle because any cycle involving some weak references will be broken once the strong reference count of values involved is 0. The weak references don't express an ownership relationship, and they won't cause reference cycle. Whenever the strong reference is 0, the weak reference will be broken. To do anything with the value that weak reference is pointing to, you must make sure the value still exists. Do this by calling the upgrade method on a weak t instead, which will return an option reference counting t. You will get a result of sum if it has not been dropped yet. So we can downgrade and upgrade. Thus will ensure that some case and the non-case are handled, and there won't be invalid pointer. As an example, rather than using a list whose items know only about the next item, we'll create a tree whose items knows about their children's items and their parents' item. We're doing a big data structure class today. We went from linked list to tree. Okay, how do we plant a tree in Rust, guys? How exactly do we plant a tree in Rust? A node with child nodes. Today we are learning data structure in Rust. Wait, hold on. Has anybody write a data structure book in Rust? Data structure in Rust. It's gonna be fun. Oh, algorithm implemented in Rust. Yes, there's this repository. Wow, what kind of algorithm do they have? They have a tree heap linked list mode. Red black tree. I can't imagine what they have been through. Geometry, dynamic programming with all of it. Fibonacci, recursive. There are like 1,000 ways to implement Fibonacci. Longest increase in subsequence. Wow. I've written an unsafe circular linked list in Rust. Wow. Wow. I don't know what's going on, so I'm going to say yes. Yes, that's all you need to say. Thank you, 50 Kalu. You don't even know what that means. That's okay. I'm confused as hell as well. So basically, tree is a data structure that has some node. Usually like a tree has a left node and a right node. It does sort of look like a tree. The tree is like, say there's a number 1. What am I doing? There's a number 1. And it has a left child, it has a right child, and then this 2 can have a left child, a right child, and this 3 can have left child and right child. It's a quite common data structure. It store information in each node. So if you connect the children and the parents, it kind of looks like a tree branch. Yeah, that's a tree. That's a tree. It's not a formal definition. And each And the leaves and nodes of the tree is made out of this basic structure of a node. You can imagine it as... How do you imagine it? It's like the basic component of a tree. Like a tree is made out of nodes, and a node has a value, integer, and one node can point to other nodes so they connect together. So yeah, it has a value, and it has children that connects together. And why the heck is it so bad? What's wrong? Did I not close? What's so wrong about my code? Oh, it doesn't have the main function. It doesn't have the main function, so it freaks out. So we add a main function, so you won't freak out. Okay, stop freaking out. Okay, so here we have a leaf, which is the lowest node. It's like the children of the children of the children, and they don't have children. No main function. Yes! Yes, no main function, and it panics. It doesn't panic, but it's oh. It just cannot accept the main function doesn't exist. So we have a leaf of value of 3, and we have the leaf doesn't have any children. Perfect. That's why it's a leaf. The leaf doesn't have more branch. It's on the base. It's on a very low point. This is a leaf. And this is a branch. It has a value of 5. And the children of this branch is the leaf above. It is the leaf. Okay, now we have a leaf and a branch. We clone the node in leaf and store that in the branch, meaning the node in the leaf now has 2 owners. So the leaf and the branch both own the node. We can get from branch to leaf through branch.children. But there's no way to get from leaf to branch. Yes, one thing about a tree is that the children doesn't know who the parents is. The parents know their children, but you see, like, the leaf doesn't have a field called parent. No, it doesn't know. The children are very shameless. The children are very shameless. They don't know their parents. That's the tree. The reason that leaf has no reference to the branch and doesn't know they're related. Okay, yeah. We want the leaf to know that the branch is its parent. What? We're making it not shameless? Add a reference from child to his parent? I've never done that. But maybe we can? Maybe we can? To make a child node aware of its parent, we need to add a parent field to our node definition. Okay, I've never done that. But I think sometimes they do that. Okay, I remember seeing the children who know their parents. Parent. We know it can't contain a reference counting because it will create a reference cycle with leaf.parent pointing to branch and branch.children pointing to leaf, which will cause their strong count value to never be 0. Thinking about the relationships another way, a parent node should own its children. If a parent node is dropped, its children should also be dropped. However, a child should not own its parent. If we drop a children node, the parent should still exist. It's like if we kill his son, his daddy still exists. If we kill the daddy, the son dies too. I know it doesn't make sense. It's more like if you take the leaf from a branch, the branch still exists. But if you take the branch away, the branch and children both dies. Anyways, so here we're using weak reference for the parents. Yabai. Clothing is yabai. Boy, do you not know that? It has always been yabai, and that's why it is so great. Wait, what am I doing? Science, wake up. The parents are weak reference. Oi. Okay, why does it not like it? So brutal. It's not brutal. It is simple. It is human natural. Human nature. Oh wait. What am I doing? Wait. Hold on. We're adding it into the node. And we need to import weak. Okay. It's over here. So weak, we need to import it. Weak. It's been 3 hours then. That's why my brain is like gradually stopping to work. Okay, now we are missing a parent. The leaf does have a parent. So the leaf has a parent. We have the new and the parent. Does the parent has parent? How did the leaf refers to its parent? Ooh. Okay, we have a leaf, we have a branch. Let's go, baby. What do we print? We print the leaf parent. Is leaf.parent.borrow.upgrade. And here we downgrade leaf.parent borrow mute. Downgrade. What just happened? So the leaf starts out without a parent. I was like, where did the parent go? So we created a new empty weak node reference instance. At this point, when we try to get a reference of the parent of the leaf by using the upgrade method, we get none. So it doesn't have anything. And then we created a parent. Oh my god. Thank you for becoming a member. That's like the first song I have heard from a few months ago. I forgot to turn on my stream alert. Thank you. Thank you, CrowFX, for joining the membership. Welcome to Neon Star. Oh, my cat is rubbing you. It's a warm welcome. Thank you. Oh. I'm going to take my cat away. You're too happy. You're too happy. You cannot be this happy. Oy. Okay, what does this do? Seriously. When we create the branch node, it also have a new weak reference to the parent field. Because branch doesn't have a parent node, we still have leaf as one of the children of the branch. Once we have the node instance in branch, we can modify leaf to give it a weak node reference to its parent. Also, here we are modifying the leaf. And the leaf.parent, we borrow the branch. We use the borrow mute in the parent field of leaf, and then we use the downgrade function to create a weak node reference to branch. When we print the parent of the leaf again, this time we'll get some variant holding a branch. Now leaf can access its parent. When we print leaf, we also avoid the cycle that eventually ended in Stack Overflow like before. Thank you, CrowFX. Thank you so much. It's fun learning with all of you. You guys teach me so much. Makes this enjoyable. And yeah, it's printing. So initially the leaf parent is none, and then the leaf parent is our branch. It's our branch. Whew. Visualizing changes to strong count and weak count. Oh my god. This is long. Let's start over.好福尼啊！晚安，谢谢，谢谢来看。Oh, okay. We still have the node. And here we're visualizing how the strong count and weak count goes up and down. So we first create a leaf with no parent and no children. We have a strong count. When we create it, we have a strong count of 1 and weak count of 0. And then in the scope, we have a branch with a leaf and no parent. And here we assign the parent of leaf to be the branch. And at this time, the branch has one strong reference and one weak reference from the leaf. and then leaf have two strong reference. Because branch has a clone of the leaf, and it still doesn't have any weak references. Yes. これはラストです。And leaf parent. Oh, after the scope, the branch is dropped, so the leaf parent is again none. And the weekend is being downgraded. Okay, I think that's all the content. Dang it, this is a long and hard stream. Initially it was all good until the counting, the reference counting and ref cell, it just confused the hell out of me. But thank you guys for helping all the way. I think I got some grasp of what strong and weak reference is, and I'm going to stop my baby, stop. Come on. Don't rub the microphone. Why? Where did you learn that? Why don't you rub the monitor? Don't rub the microphone. Come. No. Okay, I have secured. I can't. You're annoying. I've secured my cat, and we have secured today's content. We learn about smart pointers. We learn about bugs. We learn about reference counting. We learn about reference cell, mutability, dereference and drop, and weak pointers. There are so many smart pointers. I think pointers are smarter than me. What's next chapter? It's concurrency then. Tomorrow is gonna be freaking fun. When is the stream tomorrow? Yeah, the tomorrow stream is gonna be 12 p.m. Pacific time. I'm not sure how many of you can be here, but don't force yourself. Please take care of yourself first. We're going to learn about concurrency. And we're almost approaching the final project, which makes me so happy. Only chapter 17, 19, and 20 are left. And then we're done with this whole book. Thank you guys so much. I'll be looking at concurrency before the stream tomorrow. Oh my god, my cat. And yes, I'll go feed my cat again. Thank you, Vexon. Thank you. And then, thank you, underscore. Thank you, Prof. Dia. Thank you, Sayo. And thank you, Bopu. Bopu, thank you. 谢谢冰妈. Thank you, Hafnia. 晚安. Thank you, Tsue. Thank you, Kalanas of Ryzen. Thank you, CrowFX. Thank you, Batomi. You're not supposed to be awake. Go sleep. 有没有讲到？有没有讲？有没有学？学到15章了，然后18章学过，还有16、17、19和20。Alrighty, I'll go sleep. And see you guys next time. Bye bye. Thank you. Thank you, 50 Kalu. Thank you, highly intelligent Owen. Bye bye. Roberto. Thank you for subbing. See you next time.